Hello, my name is Christian Garcia, and today we'll be talking about quasi-elastic neutron scattering. So back, the limiting case of inelastic scattering characterized by energy transfer being thermal neutron scattering by Leon Van Hoek and Pierre Gilles de Guinness. In the paper, Van Hoek density fluctuations, since the density fluctuations are expressible in terms of volume of a medium, imposes a restriction on the form of its pair correlation function. So neutron scattering basics. Within a neutron, the interaction of a neutron beam with matter leads to a scattering phenomenon. The quasi-elastic region, which extends up to the phenomenon of relaxation process in the system over the whole energy range change of quanta of energy between the neutron and the sample of study. The energy transfer recipe. And here we have a diagram detailing neutron scattering. Right here it splits off while the laser points towards the set of points on the screen, on the top hand of the screen to the right, where being theta and the other being double its angle of incidence. And Q is to the right. You have different functions between which is defined below as being 4 pi since, and lambda is the wavelength being projected by the sample when it diverges. Now, or QENS. And in this, it's a limiting case of neutrons considered energy of the scattered particle. Quasi-elastic neutron scattering is the only scattering process is detonated to where the dynamics in the sample lead to the broadening of the incident neutron spectrum, small energy transfer between the neutrons and the atoms in the sample. And here we have a scattering, wherein you see at the top left, where K is directly being pointed at, where it splits off. Now, much like our neutron scattering example, only now we have this special derivative function where it's essentially the over the angular frequency of the waves. Now, well, the method of QNS enables investigation to 10 microseconds. The QNS signal is due to the different types of stochastic motions, which can be studied by QENS. We have the differential fusion, the scattering function I sub s of QT. While for localized motions, this function approaches a finite by S sub I and C of Q omega, or a constant long-range diffusion. Now we get onto elastic incoherence structure factor, one of the key structure factor in the Van Hoek correlation function, which is written as plus G sub S tilde of RT. The first term in the equation is the volume that is large in comparison to the interatomic distance of this. It gives us 0. However, if the particle motion has finite value. Now we get onto self-diffusion. As the most simple Q in coherent neutron scattering, the self-correlation function obeys partial T of GS RT, the first being equal to D sub S Lagrangian squared of GT being equal to delta of R. Thus, the diffusion process. This leads to a new equation of G sub S of RT equals 4 power times the exponential factor of R squared over 4 in spatial invariance. The spatial transformation yields the value irrespective of the details of the diffusion process value, but any long-range diffusion model converges to the Q square law at small q values of the self-coherent factor. Now, what are some of the advantages of using internuclear potentials using heavy ion quasi-elastic sub-barrier region at the energies, the cross-sections of the quasi-deviation caused by the effect of nuclear interaction? This effect, where the ratio of elastic scattering sigma sub EL angle theta, which is given by the equation, the derivative of over the Rutherford cross-section, being approximately equal to A over Ka times the square root of 2a pi sub m mass. This formula shows a deviation in the elastic cross-section of the nuclear potential, especially to the surface diffusiveness parameter. The effect of channel coupling and quasi-elastic scattering can be irrespective to the presence of channel coupling, similar to fusion energies well above the Coulomb barrier. Now we get into the comparisons between spherical and deformed neural data at deep sub-barrier energies. Optical potential to follow transmission through the barrier is simulated by imaginary potential that is in fusion cross-section, in which the elastic cross-section approximation at these deep sub-barrier energies. We define the region of a deep sub-barrier energy elastic to the Rutherford cross-section is larger than 0.94, value of the surface diffusiveness parameter of A being 0.6 centimeters. Only a few data points are available at deep sub-barrier energies. Therefore, only experimental data and channel coupling effects start an important role in the quasi-elastic reaction. Although these large values of surface diffusiveness parameter are consistent with the data systems, are model dependent as they include the deformation effect. They count surface diffusiveness parameter. The data is normalized to unity at the lowest energy. The diagram to the right is the penetrability, and we discussed the application between coupled channels and no coupling channels, and the diagonal energy, the cross-sectional ratios of spherical system solution. And as you can see from experimental data, the distance, the greater the cross-sectional ratio. And as we described, we can see that through some statistical means that the ratio. That concludes my presentation. I'll now be taking any questions if anybody has them.